Okay, so welcome back. We're going to start off with our conformations of butane, and we'll draw the molecule here. And it's important to remember that the exercise is very similar to what we did with ethane, except that we've now got two methyl groups on either end of our butane molecule. Okay, so in this first conformer, I've got one methyl group on the left pointing down, the one on the right is pointing up. I'm going to make my perspective from this side here, and I'm going to bring that right-hand carbon in front. And so when I do that, then let's label atoms as we like to do, HA, HB, HC, HD. The methyl group is going to be pointing up. That's easy. HA is going to swing over to the left, and HB will wind up on the right. All right, and then I'll draw my carbon in the back as a circle. And so the way I'm flipping it, HD goes to the right, methyl group is down, and HC is over to the left. Okay, and so we'll call this conformer A. And this is the lowest energy conformer. The methyl groups are as far from each other as they can be. They're 180 degrees. Okay, and so the energy of this conformer is taken as 0. Okay, it's the best butane can do. Okay, everything is spaced out as much as it can possibly be. All right, so then we're going to start rotating about that central carbon-carbon bond. And in this exercise, I'm going to keep the left-hand carbon fixed and rotate the right-hand one, and we'll do it in 60-degree increments. So again, when you're redrawing your structures, always start with what didn't move. And so the left-hand carbon is exactly the same. So just going to pencil that in. Okay. And the right-hand carbon now is what changed. So I'm rotating sort of in a clockwise fashion by 60 degrees. So HB is now going to be in plane and pointing down. HA is up and coming out at us, and the methyl group is back. Okay. And so I'm going to convert that again to a Newman projection, and same strategy. Let's start with the atoms that didn't move. And so if I want, I can just copy the back carbon from my first Newman projection. I don't even have to think about it. Okay. And then I need to draw the substituents for the right-hand carbon. And so the methyl group on the right is eclipsed with HD, so I'm going to draw that over here. HB is eclipsed with the methyl group on the left-hand carbon, or the one in the back, so that's here. And then HA is eclipsed with HC. Okay. So then we need to assign values to these eclipsing interactions, and we know how much this is. This is 0.9 kcals per mole. Okay. The methyl hydrogen eclipsing interaction is new, and that is 1.3 kcals per mole. And we get that twice. Okay, and so this is conformer B. And the relative energy then is 2.6. plus 0.9, which is 3.5 kcals per mole. Okay. And so we're going to continue on this path. We're going to do another 60-degree rotation. Again, redraw by starting with what did not move. And now, as I'm doing that rotation, HA is going to turn to be in plane. HB is coming forward. And the methyl group is going down. Okay. And so hopefully you can see that this has now achieved another staggered conformation. And I can redraw that in a Newman projection. So start with what didn't move, start with the back. Okay, now HA is pointing up, so that is, or HA is in plane in the line wedge, and so that's pointing up in the Newman projection. HB winds up on the left, and the methyl group is on the right. Okay, and so remember that we said staggered hydrogen-hydrogen interactions are not counted. They're treated as 0. Okay. But there's a staggered methyl-methyl interaction here that we do need to think about. And that is worth 0.9 kcals per mole. Okay. That interaction has a specific name. We call that a gauche interaction. We might refer to this as the gauche conformer. All right. And so the relative energy of this one is 0.9, and we'll call this conformer C. Okay. And so we've done 120 degrees of rotation. We're going to do another 60-degree rotation. And redraw the left first. And so now my methyl group on the right is in plane and pointing down. HB is up and HA is going back. Okay. And so hopefully you're starting to see this is going to be the worst conformer. So if I draw start my Newman projections again, HD is going over to the right. HC is to the left, the methyl group is down. Now, my methyl group on the right-hand carbon is eclipsed with that methyl group in the back. HA is eclipsed with HD, and HB is eclipsed with HC, okay? And so we can add these up. And so this HH eclipsing is 0.9, that's old hat. What's new is the methyl-methyl interaction, and you might imagine that's going to be bigger than a hydrogen-hydrogen eclipsing, and it in fact is. This is worth about 3.3 kcals per mole, okay? And so this conformer then is 3.3 plus 1.8, about 5.1 kcals per mole higher in energy. Wish there were a way to move that. And that is the highest energy conformer of butane. So I've lined up my two adjacent methyl groups. They're not bonded to each other. They're interacting. And we might call this one D, okay? And so we've gone 180 degrees, we can keep going, but the conformers wind up being the same because of the symmetry of butane. So I'm not going to redraw all those conformers, but what I'd like you to do is convince yourself that if I start with D and do a 60-degree rotation, I get back to C. If I do another 60 degrees, I wind up with B. And finally, 60 degrees further gets me back to A. Okay, so the reason you get this reflections in the energy landscape is because of the symmetry of butane. In cases where you've got different substituents on the atoms, the sort of rotational energy landscape doesn't have that symmetry, and you might wind up with 6 discrete or energies, but in this case they are the same, so we don't need to go through it again. All right, so what I'd like to then move on to chapter 3, and we're going to talk about acids and bases. And we'll first introduce some definitions. Hopefully these are familiar to you. A Lewis acid is defined as any species that can accept a pair of electrons. Okay, and for our purposes, that's typically going to be an atom that doesn't have a full octet. Okay. So a useful example of this, or common example, is what we call boron trifluoride. Okay, and the boron has a trigonal planar geometry. Okay, the bonds to fluorine are derived from sp2 hybrid orbitals on boron, and that leaves then an empty 2p orbital on boron. Okay, so if you count up electrons, there are only 6 around boron. I can take 2 more and satisfy the octet. And what we say is that if boron interacts with a Lewis base, the base can donate a lone pair into that empty 2p orbital and then satisfy the octet of the molecule. Okay. So that leads me to a Lewis base. So a Lewis base is defined as any molecule or atom that can donate a lone pair. Okay, and a good example of this is going to be diethyl ether. So So this is a common laboratory solvent. It has a 2-carbon chain on oxygen, and so that's what we call an ethyl group, so we can abbreviate that ET. And the lone pairs on oxygen are available for donation to an acid. Okay, and so diethyl ether is an example of a Lewis base. All right, so the reason I chose those two examples is because they actually are well known to react in an acid-base transformation to form a complex. And so this will be our first bona fide acid-base reaction. And this is something that we'll spend a bit of time on as we work through this chapter. So I'll redraw my diethyl ether and the BF3 on this slide. Okay, and so if we mix these two together, they interact. And let's draw the product first, and then I'll show you how it happens. Okay, so the product is what's referred to as boron trifluoride diethyl etherate complex. Okay, and we have a specific sort of formalism for showing this interaction. And what we like to do as organic chemists is demonstrate the flow of electrons in a reaction. It helps us to keep track of things. And so to do that, we use arrows. And we're going to start our arrow at a pair of electrons. So starting at the Lewis base, and have that arrow end then at the Lewis acid, at the electron acceptor. Okay, and so it's worth writing these down. The arrow always begins at electrons. Okay, and the arrow ends or points to the atom that accepts the electrons. And one final note is that I'm using a double-headed arrow, or an arrow with 2 barbs. That indicates the flow of 2 electrons. When we talk about radical chemistry later in the course, we'll use single barbed arrows. So an arrow like this indicates 1 electron. Okay, but for now we're just concerning ourselves with these 2 electron processes, which are sort of the hallmark of acid-base reactions. Okay, so what I've just shown you in the context of this complexation is the first sort of arrow pushing that you've seen, and it's important that you become adept at doing this. And so always remember that arrows begin at electrons and end at the species that accepts the electrons, the atom that accepts the electrons. If I were to draw it like this, This is incorrect, okay? Okay, so in that drawing, I'm starting the arrow like just at boron at an atom and then ending at electrons. We do not do that. So always begin with the electrons. All right, so this is an example of an acid-base reaction. And a key feature of this, again, is that the acid is able to accept additional electrons, okay? Okay, there are instances, species can still react even if they have a full octet. In that case, different types of transformations will occur. And the reason I bring this up now is because this is introduced in your book at this stage. And they introduce what's known as a substitution reaction. So I'm going to talk very briefly about that. We'll spend a lot of time on this later in the course. But I'll just say right now that if a species has an octet, other reactions occur, such as, and we'll talk about a substitution reaction. Okay, and so again, this is best illustrated with an example. So the species on the left is what's known as benzene thiolate. And the species on the right is methyl iodide. And if these two things are mixed together, a reaction occurs where the benzene thiolate substitutes the iodide. Okay, so in the product, we end up with what we call sulfide and iodide anion. Okay, so the arrow nomenclature to show this is similar, is identical in fact, except that I just can't have my electrons going to carbon because if I didn't do anything else, I'd then have 10 electrons around carbon, which would violate the octet rule. And so what I'm going to do is have my electrons from sulfur attack. Oops. Attack the carbon. Okay. As they're attacking, you might imagine then that I'm going to start to generate 10 electrons around the carbon atom, which is bad. So I need to break the Ci bond, and I push the electrons with the arrow onto iodide. So that tells me that the electrons in that bond are leaving with the iodide. Okay. And these types of reactions are very common, and they're so common that we apply specific names to the reagents in the process. So in this case, the benzene thiolate is behaving as what we call a nucleophile, and the methyl iodide is the electrophile. I think those names are self-explanatory. The I that departs is what we call the leaving group. Okay. And again, we're going to talk much more about this. The only other thing that I want to say is that remember, the charges need to be balanced. So I can neither create nor destroy charge. I have, so the sum of the charges in the starting material always has to equal the sum of the charges in the products. I have -1 on the left-hand side of the equation. I must end up with -1 on the right-hand side on balance. And so that occurs. And so that is okay. But again, we'll take a deep dive into these reactions later in the semester. All right. That concludes the first half of this lecture.